So we have formulated the Emery hypothesis testing problem to motivate this question: how much information is revealed by Y about X? And finally, in this lecture, I'll just give you the answer to this question. Well, there is no one answer to this question, but I'll give you an answer which has received, which has gained a lot of popularity. And we will go back to our initial postulate that information is the reduction in uncertainty. So we know that in the beginning, uncertainty in X is h of X. So what is the uncertainty that remains in X? Remains in X when Y is revealed. The answer to this question is something that I'll just put out before I justify it, and I'm calling this thing the conditional entropy of X given Y. Okay, I'm not calling it this thing. This is what Shannon called it, the conditional entropy of X given Y. So what is this conditional entropy? Just like entropy, this conditional entropy is defined as the entropy of the conditional distribution of X given Y, but this conditional distribution is a random variable in the sense that it depends on this Y. So what do we do with that? We just average over Y. So it's the average entropy of the conditional distribution. All right, that's what conditional entropy is, and we denote it by h of X given Y. But as we have been saying for entropy, we write it in this as a shorthand, but we write it in this form as a shorthand, but actually it's a function of the joint distribution. So this is perhaps a better notation: P of xy, the joint distribution, given Py, the conditional distribution. So namely, this is the average entropy of the conditional distribution. Yeah, that's what I wrote here. Okay. So this definition is something that I've just pulled out of a hat, and I've just given it to you. Is there any reason to believe this definition? We'll soon see that this is actually a very good definition. In fact, we'll build up quite a bit on this definition in this course. So let's try to expand this expression to understand it a little bit better. This average entropy can be written like this, and then I just expanded the entropy as summation over x, px. Now the p for x is the conditional distribution, log of 1 by px. Well, I can take this summation over x outside, summation xy, and this guy px py times p of x given y can be combined into this joint distribution. Okay, and so what do you get here? You get this summation over xy pxy log of 1 by px given y. So this we can just write it as expected value of log of the conditional distribution. Here we are viewing this pxy as a fixed function, and x and y are the random variables, and the expectation is over this distribution of x and y here. Okay, so that's what this conditional entropy is. It is the expected value of log of 1 by px given y. Just like entropy was expected value of log of 1 by px, now it's the expected value of the conditional distribution. It's an alternative expression. But we can express this conditional distribution in this form. It's pxy by py. We can write that. And therefore, since log a by b is log a minus log b, you can just write it as this first term minus the second term. And expectation is linear. So the first term's expectation minus the second term expectation. So what are these two guys? And this is very interesting what has happened here. The first term is exactly the joint entropy of what is called the joint entropy of x and y. It's the entropy of the joint random variable x and y. Second term is the entropy only of y. That's what you can observe. So what happens to x here? You just sum over all x and it marginalizes, and x gets hidden. So this is just exactly equal to entropy of y. So what is this conditional entropy? And another alternative interpretation, it is the uncertainty in xy minus the uncertainty in y. Okay, that's what this conditional entropy is. So h of xy minus h of y. That's another expression for conditional entropy. By the way, this rule that we have been using throughout is, of course, it's the perhaps it's I hope it's familiar to all of you. This is the base rule, and we've been using it in this course now, but we're using it more and more as we move forward. So just for once and all, you should just recognize this rule quickly. The joint distribution is either the conditional distribution of x given y times py, or the conditional distribution of y given x times px. All right. So we introduced this conditional entropy and saw two different expressions for it. So if you believe my definition of conditional entropy, now you should be able to define information. Okay. So how much information is revealed when you about x when you tell me y? So this is the residual uncertainty, the conditional. Um, this is the remaining uncertainty in x given y. So how much has the uncertainty reduced? Uncertainty in x minus the uncertainty remaining after y is revealed. This is h of x. That's our answer for this. And remaining after y is revealed is h of x given y. So this quantity, h of x minus h of x given y, is a very important quantity. It's the mutual information between x and y. So we had justified h of x as a notion of as a measure of uncertainty. We haven't really justified h of x given y as a measure of remaining uncertainty, but let's just believe this formula for now. But if you believe this formula, then from this postulate that information is reduction in uncertainty, we get this measure of information about x revealed by y. Okay, that's this notation once again: I for mutual information, I for information bracket x wedge y. Okay, I use this wedge notation. And another popular notation of this for the same quantity is this. The Cover-Thomas book uses this notation. This is the perhaps more popular notation, this semicolon one. But I use this wedge notation because I'll explain why this is. I'm using this notation. This notation is from the Chisser-Kerner textbook. Okay. So you can expand h of x given y as h of xy minus hy. And when you do that, you get this alternative formula, h of x plus h of y minus hxy. Same. This is also equal to mutual information. Now you can combine h of x and hxy, and you get this second new formula, h of y minus h of y given x. This is very interesting. Now this looks like mutual information between y and x. And the reason I prefer this wedge notation is because this answer is the same. It's symmetric. So mutual information between xy is the same as mutual information between yx. And this is quite counterintuitive to begin with, but slowly you get used to it, that the information revealed by y about x, according to this notion, is the same as the information revealed by x about y. Right? This is just symmetric. That's it's a feature of the notion of information that we have come up with. Okay, so there's another alternative expression for same. You can write. You can now you can verify this part, that this is also equal to h of xy minus h of x given y minus h of y given x. That's again mutual information. So there are multiple different expressions for mutual information, and you should work it out and remember all these expressions. All right. So let's notice one more thing about this mutual information. This is quite interesting. So mutual information is entropy of x minus entropy of x given y. What is entropy? Entropy is the expected value of log of 1 by px. What is the entropy of x given y? The conditional entropy. That's the expected value under the same joint distribution of log of 1 by px given y. So I can take this expectation outside and look at this expression. Now what is this expression? It's the expected value of log of px given y by px. Just because log a minus log b is log a by b. Okay. But I can write this conditional distribution as pxy xy by pyy. When I write that, I get this new expression, pxy by pxpy. So log of that. So what is this quantity now, expected value of this? This expectation is with respect to pxy. So this quantity is very nice. This quantity is a friend KL divergence. Okay, but between the joint distribution and the independent distribution. So divergence between joint and independent distribution is equal to mutual information. And what is very nice here is that information then gets related to how far in this distance is the joint distribution from a product of its marginals. So joint distribution has some correlation between x and y. This is the corresponding independent distribution with the same marginals. And the question is, how far is your distribution from an independent distribution? And that's how much information x reveals about y or y reveals about x. Okay, so this is a very nice connection between information and KL divergence. You can also alternatively express this mutual information as the KL divergence, the average KL divergence between x and p of x given y. Okay, that's an alternative expression for the same thing. So, so this notion of information we have now started to connect it to distances. Something we were looking for. We were asking if there is a notion of distance that controls the Emery hypothesis testing problem. The goal there was to understand if the difficulty of a Emery hypothesis testing problem is related to distances. But that's also related to is the information revealed by y about x related to some notion of distances. And we have some insight into this through this formula. So let's discuss this a little bit more. So given a channel W and a distribution Px on X. So you have a distribution Px on X and then you pass it through W to get Y. Okay, so Y is the output of the channel. We use the notation W of Px for the output distribution. So W of Px of Y is summation over X Px. This is the output. This is the probability with which Y occurs at the output of the channel. Okay. So with this notation, mutual information, as we just saw, is the average divergence, averaged with respect to x. Here it was y, I'm just switching it to x, of the output distribution given x, that wx, and the overall output distribution, that's w of px. Right? So this can be written as summation over x px, the divergence between wx and the averaged here. In particular, if x is uniform, then this can be written as 1 by m summation over x. X only takes these values, uniform over 1 to m. This distribution. So what is this? Now this is that geometric notion of distance we were looking for. So let's go back to our simple diagram. There are all these guys, W1, W2, Wm. They correspond to different distributions in outputs for different values of x. So what is the notion of distance here for us? It says that look at the average distribution. I'm just calling it W bar, okay? Average distribution. Look at the distance of each of them from, this distance is in KL divergence sense, from the average distribution. The average of these distances is what mutual information is. Earlier we were calling the looking at the closest one. So this is the average distances from the centroid. This is the centroid. So so this mutual information relates to this average distance, and soon we will see that the mutual information can be used to control the probability of error of Emery hypothesis testing problem. And therefore, what we get is that this average distance is a good handle on difficulty of Emery hypothesis testing. Right? So we have tied up several threads in this last few minutes. We introduced in this lecture this notion of mutual information, which we postulate captures the information revealed by y about x or x about y. Earlier, we were looking for a geometric notion of difficulty of a hypothesis testing problem in terms of distances of the underlying distribution or the spread of the underlying distribution Wx. And now what we have noticed is that geometric notion of difficulty comes through mutual information, because mutual information captures the average distance. Of course, there's a missing link. The missing link is we haven't actually related this mutual information to the probability of error for Emery hypothesis testing. And this is what we will do in the next lecture, which is the final lecture of this week. So see you in the next lecture.